Welcome back to my class, Plastic Analysis and Design. Uh, Let me make a review on what we have learned in a previous class. We already talked about the stress strain curve, especially for ductile material under tension. And beyond that, we also talk about the elastic behavior and plastic behavior of the material. And the idealized curve have already introduced also. It is elastic and perfect plastic curve, right? That is idealized curve, which is used in the plastic analysis and design. And to illustrate it, that concept, so seven examples on redistribution of stresses has been also introduced in the previous class. In this class, in this week, we are going to talk about the hinge by hinge analysis, and then some design format will be introduced. And to illustrate the hinge by hinge analysis, an example on fixed and beam with concentrated load will be introduced. And then I will give you some homework number 2. I will divide this week into 3 videos. The first video is hinge by hinge analysis, and the second video is design format, and the rest one is containing in the third video. Okay, so now we will talk about hinge by hinge analysis. It is a new concept, I think. So let's consider a fixed and beam with distribution load. As you can see in this figure, it is a fixed and beam with distribution load. As you know, this is not determinate system, but indeterminate system. And the degree of indeterminacy of this system is 3, right? 3. It means for the collapse mechanism, it needs at least 3 hinge, right? At least 3 hinge. For example, here, and maybe here, and maybe here. 3 hinge for collapse, okay? For collapse mechanism. So I will introduce step by step the hinge by hinge analysis. When the load is increased, and what happened? Of course, the first step is elastic, right? Elastic. So do you remember how to draw the moment diagram of this structure? Can you draw the moment diagram of this structure? Do you remember? It is like this, right? It is moment diagram and the total. So let's say to here, the distance or the value from here to here is WL square over 8, right? The total. You remember, right? So that is elastic. So in elastic, we have a moment diagram like this. It is the at the fixed, we have the moment is WL square over 12, and at the middle, the moment is WL square over 24. If the load is increased, and what happens? If the load is increased, then the hinge, the plastic hinge, will be occurs here, will be occurs at both fixed, because the moment at the fixed section is double higher than in the middle. So the hinge, plastic hinge, will occurs here first. So we have two plastic hinge here at elastic limit. Elastic limit, we have two hinge at the fixed. So because this is plastic hinge, it means the moment here now equal to mp. So mp means the plastic moment or plastic strength of the section. Okay, mp is plastic strength of the section. So now we have wyl square over 12 equal to mp. Wy is the load at elastic limit. Okay, the load at elastic limit. So now from this equation, then we have sigma y equal to 12 mp over L. Again, Wy is the limit load, elastic limit load, elastic limit load. Okay. Then what happened next? Elastic, plastic, elastic, plastic. In this phase, the hinge is occur at both ends, so it has mp. While at the middle, m is smaller than mp. M smaller than mp. So we call it is elastic plastic. This section is elastic, but this section is plastic. We have two plastic hinge already occurs. And keep increasing the load. We have collapse phase. At the collapse phase, the hinge should be occurs at both ends and at the middle as well. We have three hinge. Okay, we have three hinge. Then it's collapse. It means not only MP here, but now also we have MP here at the middle. Okay, so remember in the previous week we already talked about the idealized curve. Idealized curve, okay? So elastic and plastic. So elastic means this part, and plastic means this part. What does this mean? It means if a section is plastic or has plastic hinge, then the moment is remain, right? It is remain. The moment MP is remain. Then although load increase, but moment of the section is not increased due to the idealized curve assumption, right? It then the load increase, then the moment at the middle section increase until MP. Until MP. Now we have here MP and here is MP. Then we have 2 MP. 2 MP. And it always has the total moment is WL square over 8. Okay, W square over 8. WP means the collapse load. Okay, the collapse load. WP is collapse load. Now we have WM that WP L square over 8 equal to 2 MP. Then collapse load equal to 16 MP over L square. Okay, 16 MP over L square. So now we have WY and WP. WY equal to what? 12 MP over L square, right? 12 MP over L square. And WP equal to 16 MP over L square. Okay, so based on the previous analysis, now we can plot the load and deflection curve. The load deflection curve, or this is load deflection curve. Load deflection curve, okay? Load deflection curve. This is distributed load deflection curve. In the elastic state, we have a linear relation between the load and the deflection. It is linear state. At this point, it is elastic limit. Elastic limit. At this point, at this state, 2 plastic hinge occur, right? And at this corresponding to this point, the elastic limit load Wy equal to 12 MP over L square at this point. And the corresponding deflection is dy. And just keep increasing the load, then we have the third state. And this is elastic plastic. Elastic plastic, right? There are 2 plastic hinge occur. While in the middle, the moment is smaller than MP. And at this point, it is plastic column. Plastic column. Okay, plastic column. At this point, 3 plastic hinge occur. Okay, 3 plastic hinge occur. 2 hinge is at both ends and 1 hinge is at the middle. Then the collapse load equal to 16 MP over L square. Okay, and the corresponding deflection is dp, delta p. Please note that the actual initial yielding is at this point. Okay, is at this point due to the redistribution of the section. Okay, you remember? For example, if we have a section like this, rectangular, and in the plastic phase, the stress curve, stress diagram is like this. It is stress, and the initial yielding sigma equal to sigma y is start at this point. But at this point, it is fully plastic of the section. So at that point, the section is fully plastic. Okay, this is sigma y, and this is sigma y. So this is fully plastic of the section. It is initial yielding. So the actual point, actual initial yielding is here, corresponding to this state, sigma equal to sigma y, and this part is still in elastic. Okay, but at this point, it is fully plastic of the section. And one more thing is the ratio between collapse load and elastic limit load equal to this ratio. So you can divide this over this equal to 1.33. Okay, so we have a gap between the elastic limit and plastic collapse load. It is a gap. The gap is due to the redistribution of the internal load, internal force. Okay, this gap or is reversed due to the redistribution of the internal force, because in the intermediate system, okay, there is a distribution of the initial force, and due to the initial force redistribution, we have a gap between the elastic limit load and plastic collapse load. In this case, the ratio is 1.33. Okay, 1.33. So now we can see, we can understand the difference between plastic analysis and elastic analysis, right? Plastic analysis and elastic analysis, they are different due to redistribution of the force and of the stress. Okay, so I hope that you now you can understand about the concept of plastic. About the hinge by hinge analysis. That is a hinge by hinge analysis. Step by step, you can consider the load and the hinge, plastic hinge occur procedure, and you can calculate the elastic limit load and the plastic collapse load. in some case, the elastic collapse load and plastic load may be equal. It depends on the boundary condition. Okay, it depends on the boundary condition of the structure. In terms of moment curvature, it is moment curvature curve. This curve is idealized curve of moment curvature, but the actual curve is like this here. Okay, actual curve is like this. So let's say from so elastic phase until elastic limit point, it is linear relation between moment and curvature. And at this point, we have my, and my equal to sigma ys. And you know sigma y is yielding strength of the material. And S is the elastic section modulus. Z is plastic section modulus. And we have my, elastic moment equal to sigma y multiplied by S, and mp equal to sigma y multiplied by Z. And mp greater than my. Of course, mp is plastic moment greater than my, and my has a gap. This gap depends on the section. Then the ratio between the plastic moment and elastic moment is called safety factor F, and F equal to 1.12 for H section or I section. Okay, H section. If for rectangular section is maybe 1.7 something. And it depends on this different section. We have different ratio between MP and My, and this curve is already introduced in the previous week, right? And you understand the shape factor. And this actual curve, due to the resident stress in the section, right? And some other factors, and we will talk about the effect of the different factor into this behavior of the moment curve in some next class. But normally it has not idealized curve like this. Okay, so we already talked about the hinge by hinge analysis. And I hope that you understand very general about hinge by hinge analysis procedure. And from now on, many problems will be discussed by hinge analysis. Okay.